Good day. In this tutorial I will show you how you can prepare a standalone Python script that will create the set special quasi-random structures using the Python package ICET. In my previous tutorials I illustrated how you can use interactive interface of simply SQS to create such structures but with AT-AT code. But if for whatever reason you prefer the ICET code, I created a similar interface where you can set the search parameters. Okay, so let's briefly illustrate how it works. First of all, you can use this interface on the interactive website on this link, which I will put also in the description of this video. And then you need to create a virtual environment and where you will run the created standalone Python script, and in this environment you have to install these necessary packages. Once you have these packages, then you can run the code. Okay, I already installed this, so it should be simple how to do it. And let's create now, for instance, high entropy alloy with some 4 elements starting from face-centered cubic structure. So I downloaded a zip file for copper, which I will upload here, and it will define the initial atomic positions and the initial lattice parameters. Then I have to select which SQS search method I want to use, so I can either specify the keeping the set supercell size and shape fixed, and other option which is currently implemented is the enumeration, which can find the global most randomized structure, but this scales very poorly, and I think you can use it for, let's say, structure with 8 atoms at maximum. Then I can define if I want to perform the search in a single run to find only one special quasi-random structure, or I can use multiple runs to find, let's say, for instance, 6 independent structures. Other parameter is that I can search for these SQS in parallel, which is defined by this number, and it depends on how good CPU you have with how many cores. So for instance, if I set this as 3, I will search parallel for 3 SQS runs, and then once they are finished, for the second 3 runs. And and then I can define the parameters for the clusters, so for the pairs and for the triplets. For illustration, I will use it like this, for instance, 4 angstrom for pairs and 3 angstrom for triplets. And this determines the number of Monte Carlo steps that are used during the search. So for the illustration to be quickly finished with the calculation, I will set 20, let's say 20,000 steps. Then if I have a structure which have multiple sublattices, I can specify the concentration on the sublattices, or I can use or treat all the atomic sites equivalently and search for set global composition. So for this case I can use the global composition, and then I can define the shape or the size of my supercell. So for instance, let's set it as 3 times 3 times 3, which will have 108 atoms. And then I can define the composition. If I want to have a vacancy, I can use the symbol X. So let's say I will define cobalt, manganese, and I don't know, silver. Then I can set the specific atomic fraction over each element. So if I want to have it the same for all of 4 elements, so 25% each, and that's basically it. So now I can generate the standalone script that will perform this search. And okay, so here you can also define which structure format you want to save as the SQS, like for the found SQS. Then this parameter defines how often you want to print information into console and into which directory you want to save the results. So this will save it directly where I will place this script. And now I can either download the script or I can copy its content and put it into my console. So I tried it before. I deleted data already, and if I do it now again clearly, so let's create the Python script. I can call it like run search with the Python extension and insert the content here, then save it with Ctrl S, close it, Ctrl X, and now I can run this script. So it started, and you can see it started parallel the three independent runs, and this shows you how many steps, the Monte Carlo steps, are already done in percentage, and this is the best objective function for each, like within each run. And once this is finished, it will plot me like the time dependence of the objective function into the output folder, and also how the how the correlation functions are matching. And it started the 3 remaining parallel runs, which you can see here. So soon it will be done. And yeah, it also automatically save the best structure for each run in the defined postcar and CIF format. Okay, so everything is done, and now I can see the results, and I refresh this folder. So here I have the objective functions over time. So this is like these are all the objective functions from each run, and this is the run number 1, like across all steps, and then zoom on the last 20% of the steps. So here nothing changed during the last 20%. Here is the run number 2 with the last 20% of the steps, and I can see there is some change. And run number 3, 4, 5, and 6. And then here in cluster vectors, I can see individually it's better how each cluster vector is matching to the perfect random alloy for each run again. And here is like all of them in one graph. And the last one I will show you are the safe structures, which are here, which I can visualize, for instance, in Ovito, and then use it for subsequent simulations. Okay, so that's all, and I hope this will be this interface will be useful to you, and also you don't need to only use the ICET, you can use the AT-AT interface in the simple SQS. So thank you for your attention.